which means you're also going to have to know how to rationalize radicals, and we'll talk about what that means in just a second here. So how do you multiply radicals? Well, this is how you do it. Step 1. You multiply...
Wait, did you get any thing?
No. I'm just using an old one that's falling apart.
No.
My grandma has some.
Go ahead and bring them to me if Graham has some. Okay.
Graham. Is that what you call your grandma?
No.
What's up, Graham?
Well, one of my grandmas is no longer alive, and the other one is, like, doesn't even know who I am anymore. So, thanks, Rob.
Thanks.
Well, geez, sorry.
All right. You're going to multiply outside numbers together and the numbers underside the radicals together. I'm just joking, Rob. It's fine.
Gosh, that made me feel bad. I'm having a good day, too. Gosh.
I'm literally laughing. It's not a big deal.
Really just made me feel
That's what I do. When people are like, oh, where's my grandma? I'm like, she's dead. They're just like, whoa. I'm like,
So you'll multiply the outside numbers together and numbers under the radical together. The basket is coming out.
only the basket.
It wasn't me for once.
Only the basket to people that.
Yeah.
If I see it, the basket is out. All right. So multiply outside numbers together and the numbers underneath the radical, and then do the factor tree to simplify. Oh my gosh, you have space above and below your slide that I don't have. So use that.
Who, like, decided that they wanted to do this?
Probably me, let's be honest.
You decided you
Oh, I thought you meant this thing. I ignored what you
like a
said.
mathematician.
No, what mathematician? I have no clue.
Yeah, like.
I don't remember. I did take a history of math class in college. But I don't remember anything from
what
it.
you
That
learned.
sounds so boring.
By the way, Miss Brady, wait, hold on.
Or infinity, or like invisible numbers. What is the thing that I hate? Invisible numbers.
They're not
What?
called invisible, they're
What'd you-
imaginary.
You saw it? How?
You literally were texting them, threw it in your pocket, put it in here.
Alright. That's unfair.
It's not unfair. It's true. We'll talk about that. We'll talk about that. All right, guys, let's get through the notes. So, technically, there's no numbers outside, so we multiply 1 times 1, essentially, which is still 1, and then, what'd you say?
What? 15.
Yeah, the square root of 15. From there, we attempt to simplify it, but do we have any partnerships there? No, so that is just the square root of 15. All right, example 2 is a little bit harder. Example 2 is a little bit harder. Do you guys see that parenthesis with an addition sign in there? So that means we have to use the distributive property. What is outside of the square root of 2? What's in front here? So just think of that as a 1. So we first do the square root of 2 times the square root of 8. Logan, what's the square root of 2 times the square root of 8? Okay, then we do the square root of 2 times 4 square root of 3. Rob, what would the square root of 2 times 4 square root of 3 be?
I'm not following, sorry.
So outside numbers together. So there's a 1 out front here, right? 1 times 4 is?
4,
So that stays 4. 2 times 3 is?
6.
Okay. Do you see that?
Yeah. I wasn't really paying attention.
You're fine.
I was in my own world.
So from there we have to do our factor trees. So the square root of 16 is? Hayden, what's the square root of 16? 4, because we have 2 groups of 2. 2 times 2 is 4, nothing left over, which means we don't have a radical anymore. Can we simplify the square root of 6 if it's 3 and 2? No. So this is just 4 plus 4 square root of 6. Can you combine those? Are those like terms?
No.
Nope, so there's your answer. I do not.
No, don't even do that to Logan. He ain't even on it.
He's fine. It's just right there. I haven't seen him touch it yet. All right.
Why are you trying to do him like that, dude?
Okay, guys, focus. So now we have to use the extended distributive property, which means 2 root 3 needs to go to both pieces of the second, and radical 5 needs to go to both pieces of the second parenthesis. So everything from the first needs to be distributed to everything from the second. So Kylie, I have 2 root 3 times the square root of 10. And remember, in front of the square root of 10 is a 1. So what does that become?
2 square root 30.
So yes, that is 2 square root of 30. And if I do 2 root 3 times 4 root 6, what would that be?
8.
You're good. How you said it was fine. Gabe, there's a 1 in front of the square root of 5. Square root of 5 times square root of 10 is? But the negative doesn't go inside the radical. Is that negative underneath the radical? So it'd be just the square root of 50. What is out front of that? A negative. Because a negative 1 plus times a positive 1 is a negative 1. So that's where that came from. There's a lot of talking going on today. Please stop. Negative root 5 times 4 root 6, Greg. So negative root 5 times 4 root 6 is?
Wouldn't that be negative 4 square root 30?
Yep. So then we do our factor trees and we'll simplify from there.
Wait, what's that?
What?
Could you combine the 2 square root 30?
Yeah, I'm just seeing if they can simplify first before I combine them. But they won't. So those two don't simplify, so I have 2 root 30. Daniel, what does,
Would it be negative 2?
I haven't combined those two yet.
Oh.
I'm just doing this part right now. But yes, it will get there. Daniel, what does this one simplify to? It's not root 3, be careful. The 3's are the pair, what's left over? Good. You two. Do you need to go to the nurse? Do you have food? You can eat.
I'll give you a granola bar.
Desiree, how does the square root of 50 simplify?
I like you.
Do you, what? So be careful here. How many 5s do we have? 2. So we can take one of those out, so that becomes a 5 out front, and then it's radical 2. And then this one can't simplify. So then we will combine our like terms. So as we have already noticed, these two are like terms. And these two happen to be like terms as well. So what is my final answer then, Kylie?
Negative 2, radical 30, plus 19.
Radical 2, yep. Okay, please be careful about using distributive property. The only time you use distributive property if you see addition or subtraction. So, Rob, it sounds like you've already done number 4. Tell me what you did first.
The outside numbers first.
Which was?
12.
And then you did what?
I multiplied the inside.
Which was?
45.
Okay, then what did you do?
And then I did the little tree, factor tree for 45, and then 9 and 5.
Yep. So what did that become then? Okay. Devin, what would that answer be then, from there? After we simplify. Yes. So, Rob, do you understand why this is 36 square root of 5? Okay, so do you see how there's a group of 2 3s?
Yes.
So we take one out.
Okay.
So 3 times 12 is?
36.
And this one doesn't have a partner, so it stays under.
Okay.
Does that make sense?
Yes.
Okay. We're not going to do the whole try it, so let's skip that. I would like to get through notes. So I'm on dividing radical numbers. Why do we rationalize? So the quotient property of square roots. The square root of a quotient equals the square root of the numerator and the denominator. So this is saying if you have the square root of the whole entire, a rational number is a fractional number. So if you have the square root of a rational number or a fraction, all that means is you're taking the square root of the numerator and the square root of the denominator. As long as a is greater than 0, greater than or equal to 0, and b is greater than 0. So first of all, why does a have to be greater than or equal to 0? Meaning that it has to be a positive number. Why does the number underneath the radical have to be a positive number in the numerator? Yeah.
Because you can't have negative square roots.
That's where the imaginary numbers that Kylie was talking about come in. So when you have the square root of a negative number, it's an imaginary number. And you'll talk about that next year. But the square root of a negative, watch yourself over there, Logan, I can see you. You guys need to realize that it's because when you do the square root of a number, like the square root of 16, it's the same number times the same number to get you there. Well, 4 times 4 is 16, or negative 4 times negative 4 is 16. There's no way to multiply the same number times the same number and get a negative number, because one has to be positive and one has to be negative. So that's why it's like that. So this one's a little bit different, though. It doesn't have or equal to. Why can't b be 0? Why can't the number in the denominator be 0? Think about slope. It would be undefined. So if you think about slope when you do like 1 over 0, remember we said it's okay to have 0 on top, but NO is what I always did for you guys to say that it would be undefined if you have 0 on the bottom. In math, you can't divide by 0. I think some people have asked Siri like that question and talks about like a cookie monster or something or whatever, right? Isn't that like Siri's thing? So it kind of explains why you can't do that. So, but for example here, the example here is the square root of the whole entire thing means you're taking the square root of 3 and the square root of 4. Well, the square root of 3 can't be simplified, but the square root of 4 is 2, so that's your final answer. So that's kind of what we're going to be looking at here. But sometimes the radical in the denominator does not simplify. So sometimes we do not have a radical that can simplify. In this case, we have to rationalize. The problem is you may not leave a radical in the denominator. He does not. So you may not have a radical in the denominator.
That's
beautiful.
solid. That's like solid.
It is. So what that means is we rationalize. So we have the square root of 5 over the square root of 3n, which equals the square root of 5 over the square root of 3n. Because we can't simplify it, we have to get rid of the radical underneath. So we're going to multiply by the square root of 3n over the square root of 3n. Why can we do that? What is the square root of 3n over the square root of 3n? 1. If you multiply something by 1, does it change the number? No. So it's because you are multiplying by 1 which doesn't change the number. We are having a huge issue with talking, and it needs to stop, please. So, you'll notice that we are just multiplying by 1. Square root of 3n divided by the square root of 3n is just 1. If you multiply by something by 1, it never changes. So as long as you're multiplying by the same thing in the numerator and the same thing in the denominator, it's okay. Now, what happens when you do that? So this is called rationalizing, because we can't have the radical in the denominator. Well, 5 times 3n is 15n, and 3n times 3n is 9n squared. Well, when we go to simplify, and then that's n times n, right? N squared is n times n. Do you see that? So 9 is 3 times 3, and n squared is just n times n. So we have groups of 2 there. We have a group of 2 3's that we can take out, and a group of 2 n's that we can take one out. If we take everything away, do we have a radical anymore if there's nothing left over? No, that just becomes 3n, which gets rid of this. Now, be very careful. Do you notice how this one's inside of a radical and this one's outside of a radical? Do you guys all see that? Some of you guys are going to take one more step and say that's just the square root of 5 or something like that. But can you divide something that's inside with something that's outside? No, it's just like multiplying. We only multiply the outside pieces together and the inside pieces together. Do not divide like radicans with constant numbers that do not have a radical at all. All right, so just be very careful there. So let's get to work on that stuff. So first of all, we can't have a square root of 3 in the bottom, so what are we going to multiply both numerator and denominator by? Looking at the example from before, we multiplied numerator and denominator by what was in the denominator, because then it created pairs. It created 2 3's and two n's there. So what are we going to multiply numerator and denominator by in this one here? Yes? And that's just 1, so that's why that's allowed. So we get the square root of 30 over the square root of 9. And we do our factor trees to try to simplify. So, Iku, what would that simplify to then? Can you simplify the square root of 30? No, so that stays square root of 30 in our numerator. Rob, make sure you're paying attention. And what does the square root of 9 simplify to, Iku? 3. Can you divide the square root of 30 with 3? No, one is under a radical and one is not, so be careful not to combine those. How could I rewrite the square root of 7/3? What is another way to write that? What is the other way we could write that? So let's go back 2 slides. If it's the square root of the whole fraction, you can take the square root of the numerator and the square root of the denominator. So, how would we rewrite that? Casey? But there's a problem. What is our problem with this? Are we allowed to have radicals in the denominator? No, Olivia, so what are we going to have to do? And it just happens to be the same thing as the one above. If this could have been like a radical 5 here, then we would have done radical 5 and radical 5 there. All right, so just be careful there. So you multiply straight across. You are multiplying by 1, and that's why it's allowed. Okay, that's why you can rationalize this too. So we multiply straight across. When I multiply straight across here, Greg, what does the numerator become?
21.
And square root of 21 and over the square root of 9. So then we do our factor trees. Morgan, does my numerator simplify at all? No, so that's square root of 21. Does my denominator simplify? Can I divide the square root of 21 with 3? No, one's inside of the radical known as the radicand, and the other one is outside. It's a constant. Emma, what do you know about 2 and 6? What could you do with 2 6? You can simplify that. What does 2 6 become? So this is the same thing as the square root of 1/3. How could we rewrite that? How could I rewrite that there, Hunter? How could I rewrite the square root of the fraction 1/3? Like we did on number 2. So we said the square root of 7 over 3 is the same thing as the square root of 7 over the square root of 3. So we just simplified 2 6 to 1/3. So how could I rewrite that? Okay, we have an issue. What is my issue? What is my issue? You have a square root or a radical in the denominator, right? So that is an issue we have here. So Katie, what do I have to do? Yeah, we need to stop using the square root of 3. So the numerator becomes the square root of 3. The denominator becomes the square root of 9. There's no tree for that one. So Lindsay, what's my answer for the example 3 then?
Square root of 3 over 3.
Yes, and please do not simplify that to 1. One's under the radical and one is not. All right, example 4 is a little bit different than what we've been doing. There is a radical in the denominator, which is not allowed. We cannot have that, but we have a 4 out front. Yeah.
Do we have to, like on the number 3, did we have to simplify it? Could we do it without simplifying? Or would we have to, no matter what?
Yeah, you would just have to simplify, like when you did the factor trees.
Like 1/3, you know?
Yeah, so you could have done it. You would have multiplied both top and bottom by the square root of 6. But the problem is when you did that, you would have had, like when we did the factor trees here, there would have been more work within the factor tree part. So if you simplify up front, it makes it a little bit easier in the end. But it doesn't matter. You could simplify either up front or at the end. It doesn't matter. Yeah.
Okay, I'm just confused by like what we multiply by. Like
You-
when we cut multiply by 3, like I was confused.
It's just because it's what's in the denominator. So do you see how, like, there's a 3 in the denominator and we want to get rid of the 3? So think about this. So to get rid of a radical sign, you need a pair, right? Like when we do like our factor trees, we're always looking for the pairs. So for this here, to get rid of this to be square root of 3, we needed to have a pair of 3's. So if we multiply it by the square root of 3, it creates a pair of 3's. Does that make sense? But whatever you do to the denominator, you must do to the numerator. So it just all happened to be 3's. This one's going to be a little bit different. So we'll go for this one, and then I'll explain it again.
To get red.
I'm sorry. I talk weird sometimes, or all the time. So what do you guys think we're going to have to multiply by? I really need to change this.
3, this first.
Yeah, you don't need to worry about the 4. Is it okay to have a constant in the denominator?
Yeah.
You have numbers like 1/2 and 1/6 and 2/3, right? We have whole numbers in the denominator all the time. The problem is the radical. So all you have to multiply is by the radical. So that is what we'll do here. So what is in the denominator then, Jill?
4? Oh.
Yeah, 4 root, not 3.
Oh, 9.
3 times 3 is 9, right? And what is in the numerator, Abby?
5 or 3.
Good. So then we look to simplify our radicals. And what is my final answer, Ian?
Should be 5 out of 3.
Be careful. I know why you got 7, because you took the 3 out, right? But we don't add them, we multiply them.
12.
Yeah, so square root of 9 becomes 3. 4 times 3 is 12. I know where you got the 7 from. So you had the right thought process. It was just that one little thing. It depends. I need to look at what the next examples are.
It's just like the same stuff.
I just need to make sure there's no addition or subtraction. Let me look at the homework real quick, too. And yes, I will give it to you if that's the case.
Wait, are you sure this time you're not having what?
We are done. I'm going to get you guys your homework. What did you just say?
Are you sure?